In this video, we're going to take a look at a special kind of binary tree known as a heap. So, as we've discussed so far, a binary tree is a tree that has at most two children for every single node, right? So any given node in my tree can have at most two nodes connected to it, which we call the children. In our binary search tree, we had this additional property that the thing to the left of a node was smaller than it, and the thing to the right of a node is bigger than it. In a heap, we don't have that property. So a heap is just a binary tree. It's not a binary search tree. So we maintain the property that every node has at most two children, but there's no requirements for the children to be of any particular value. Now, the important part of the heap structure itself is that we have one requirement for the root of the tree. We say that the root of the tree has to be either the maximum value in the heap or the minimum value in the heap. There's basically two different implementations. We could say a max heap, which is the root is the biggest value, or a min heap, where the root is the smallest value. For our videos here, we'll be discussing a max heap, since it's the main one that we're going to be using. However, you'll see that getting to a min heap from max heap is a pretty easy implementation change. So by the end of this, you should also be able to make a min heap as well. So that's the idea, is that we want to get a binary tree, and that binary tree always has the largest value at the root. Now, when we get to the question of representing this tree, we could use those node objects that we were using with our binary search tree. However, there's a way to simplify matters to make the representation of our data a bit easier. What we can do is we can assert one additional condition, and that condition is that the tree is going to be populated in level order. So because there's no requirement for, the left and right values to be, smaller or bigger than their parents, we can instead say that when we insert nodes, we want to start with the root, then we want to insert everything that's at the next level, and then insert to the next level starting from left to right. What this does is it creates what we would call a mostly complete tree. Basically, we insert the root first, then we insert the level under it, and then we insert the next level, and we're always inserting from left to right. So for example, this would be a valid heap, but we wouldn't really consider this to be a valid heap because we've inserted to the right instead of inserting to the left. We should populate the left first, and then populate the right first. Right, so for example, this would be a valid heap, but something like this, we wouldn't really say is valid heap. These two nodes should be on the other side because we want to generally insert from left to right. And you might be wondering, well, why would we do something like that? And the reason is that it actually makes it very easy to represent our heap using just an array, which is very helpful because keeping track of a large number of nodes can be pretty complex. So if we can store things in just an array, that's really nice for us. So to demonstrate this, I'm going to show you an example heap. So largest value is the root. And then from there, everything else doesn't really matter what those values are. We can just kind of insert them wherever we would like, so long as we follow this property of inserting from left to right and inserting each level at a time, right? So this right here would be a valid heap for us. What we can say to store this inside of an array is we can start with our root and say that it's the first element inside of the index. And then what I can say is that for any given parent node, the left node to that parent would be located at 2 times the parent index plus 1, and the right would be located at 2 times the parent index plus 2. So what that means is that, so 20 has an index of 0. To find its left child, I take 2 times 0, which is 0, and then I add 1 to it, which means that it would be at index 1, in this case, 15, right? Similarly, the right would be at 2 times 0, which is 0, plus 2. So it'd be right here at index 2, so this would be the value 10. Now we could do this for each of the other nodes, right? For 15, its left child should be located at 2 plus 1, which is index 3, right? So that'd be the value 3 right here. The right of that would be at 2 times the index plus 2, so that would be 2 times 1, which would be 2, plus 2 would be 4, right? So 4 would have the value 4 inside of it. And then finally, for our last node here, 10 has a value of 2. Its left node must be at 2 times 2, which is 4 plus 1, which is 5, right? So be located right here. So do you see how we can easily find the location of any node using this simple little formula here? So this would be the idea of how we can reference our data. Now, I'll also note is that we can go backwards, right? So if I start at a child, I can also find its parent. So if I start at, say, index 4, and I want to find its parent would be 15. The way that I get to the parent is I just take the index and I divide it by 2. And generally, I should convert this to an integer, so I'll put the 2 slashes here to say that we convert it to an integer or round down the result, right? So in this case, 4 would be divided by 2 to get 2, so this would have to be generally the parent. Oh, sorry, because it's 0 indexed, it would be I minus 1 divided by 2. Sorry, so if I divide 4 by 2, after subtracting 1 from it, it would become 3, which when we divide that by 2 becomes 1. So that gives us 15 as a result, right? Similarly, if I had the value 5 and I were to subtract 1 from it, it goes 4. When I divide that by 2, I get 10, which is the parent element here. So we can see that this does actually work for us to be able to find each of these different elements. And what you'll see is that we can implement this very simply just by using an array and using these various different calculations to maintain our array properties. So this for now gives you a general intuition of how the heaps work. In the next video, I'm going to demonstrate to you how we can insert values into a heap, how we can remove values from the heap, and we'll take a look at some applications of the heap itself. So thanks so much for watching, and I'll see you in the next video.